So this lecture, we're going to lay down the foundation of the statistical mechanics treatment of macromolecular systems. So after having laid down the foundation of what we mean by molecular mechanics, which basically is solve a Schrödinger equation where the energy corresponds to the Born-Oppenheimer surface, and then use Newton's equation to integrate the motion forward of the system, I would rather say use Hamilton's equations for reasons that will become clear in a moment, but of course Hamilton's and Newton's equations are completely equivalent from the point of view of physical content. Now we address the problem of really trying to describe molecular systems in practice. And already at the end of the last lecture, we began to mention that typically anything we use to measure a physical system has a time resolution that is rarely that of the femtosecond, right? And also spatial resolution that doesn't allow me to monitor instant by instant, femtoseconds by femtosecond, the motion of each individual atom in a macromolecule, and probably their velocities, right? So this is telling me that even if I can solve these equations, so notwithstanding the problem associated with numerically solving the equation, which we will deal with, I come across the problem of, one, not knowing the initial conditions from which you solve the equation, and two, not being able to test the solution, because even if you knew all the initial conditions of all the atoms in the molecule, and even all the atoms in the solvent, assuming we have a solvent description, well, we will need to test it by measuring the same information at some later time. So clearly, this is not something that we can do, nor we can possibly we are even interested in doing this. There's far too much information that we are not really interested in. If I'm interested to understand how a protein folds, I'm not particularly interested to know what water molecule number 5252 is doing at the 57th femtosecond, right? So clearly, there must be some kind of averaging involved in understanding macromolecular dynamics. So the moment you start talking about averaging results of integrating Newton's equation, you are in principle linking physics to statistics, and the result of linking physics to statistics is, of course, statistical physics. So this is the moment where we actually stop being focused on a single particle with a single initial condition and asking what equation does this macromolecular system follow, and we start addressing the question how we really describe a complex system. What we said last time, just to introduce the argument topic, was that we can think about the most straightforward way in which we actually can average to extract information is that of a time average. We start from some initial configuration and let this be an observable evaluated as a function of position and momenta. And if we evolve in time, we will see these observables performing the trajectories, possibly showing different regions. And probably when we measure these observables with an experiment, we have a finite time of resolution large delta T, right? That is likely to be larger than the femtosecond. So clearly, when we measure this system, we implicitly are measuring a time average over a time interval delta T. So first of all, it makes a lot of sense to define a time average, which is the integral from 0 to big T of of the microscopic observable as a function of the phase space coordinates divided by the time interval. This is called the time average, right? So, during the last lecture, though, we flew upon the idea that you can think about a different average, which we will return to today. That is the phase space average. So now let's try to motivate this idea of connecting time averages and phase space averaging more precisely. You see, the problem with doing time averages per se is, first of all, you have to know the dynamics of the system for a long time, which makes this average meaningful, which, of course, in principle, we can do, so we don't worry about computational limitations at this stage. We will later. But the real problem is that we don't know the initial condition, at least not for all the degrees of freedom in my system. I'm probably repeating concepts that you have seen in your statistical physics course. I'd rather repeat half a lecture of well-known concepts than start off with something that is more advanced, so that I'm sure that the language that I'm giving is the language you can rely upon, okay? And of course, if you have the impression that I'm covering material that for some reason you didn't cover, it's a good time to stop me, okay? Anyway, this point here is the initial state of the system, is the observable computed at the initial state of the system. And the observable computed at a later time comes from taking the initial state of the system, evolving Newton's equation, right? And recomputing after whatever time we want, the observable in a new phase space configuration, right? But you know that in order to evolve Hamilton's equations and Newton's equation, you need the initial velocities and the initial positions. Do you know the initial velocities and positions for all atoms in a macromolecular system? Clearly not. And so, what is this? What can we do with time averages? Well, it's difficult to say, right? Because in principle, we would need to know all this information which we don't have. And here comes the magic, fantastic idea that Boltzmann and Gibbs used to basically define statistical physics. And the idea is, well, I don't know the initial conditions. But I can imagine that if I repeat the calculation for different sets of initial conditions, I will basically generate copies of the evolution, right? And if the copies of these evolutions evolve for long enough, and I stress evolve for long enough, for reasons that will become clear in a moment, they will provide equivalent pairs of momenta and positions for my systems, alternative states in which my system can be found. So in a picture, suppose I start from a slightly different initial condition, so now it has a slightly different position, a slightly different momentum, and I repeat the same process. Now you see, you generate an entirely different trajectory. So now your time average will be different. Okay? But the idea is that, suppose now, let's go back to really a phase space representation rather than an observable time series. Okay? And try to understand better what's going on in a phase space diagram. So a phase space is a high dimensional space. Of course, I cannot represent it on a blackboard. It's the space of all positions and all momenta. And the way I like to represent it is borrowing from my professor of analytic mechanics back in the day, where he was using this notation, which simply reminds me that this is.
It's possible to draw on the lines for the
Sure. If I can do that, I'd be glad to. Okay? So the initial condition, so here I'm condensing all positions in one coordinate and all momenta in one, but these multi-error down here are there just to remind me that this is a cartoon, and what my mind cannot do is represent a 500,000 dimensional space. So my initial condition here would be a point in phase space. So actually, if I use the notation P and Q, I should put P's on the X and Q's on the Y. It doesn't really matter, because I'm using P and Q here. Okay, so the momenta on the x-axis and position on the y-axis, it doesn't really matter, of course. You can permute axis as you want. Whatever discussion I'm doing doesn't get affected. So my initial condition is a point in phase space. Now, my Hamilton's equations, or if you want Newton's equations, can be written as a pair of one-dimensional, first-order derivative, where the p's are simply negative, the partial derivative of a Hamiltonian with respect to the q's. Remember that? Which is nothing but Newton's equation, by the way. P dot is the acceleration time mass, and this is the gradient of the potential. And the q's are P divided by M. So they can be written as the derivative of the Hamiltonian with respect to the p's, right? Where the Hamiltonian is P squared over 2M plus U of Q. Well, this is a bit of a stretch. If you go back to your second year, the Hamiltonian is derived from the Lagrangian through a Legendre transformation. So it doesn't necessarily have to fill in this form. If you have constraints, if your dynamical variables are angle or whatnot, we will assume we're doing Cartesian coordinates, and the Hamiltonian will be this, and which makes the connection with the Schrödinger equation very clear, because this is really the classical Hamiltonian that enters the Schrödinger equation. All you have to do to go from classical to quantum mechanics is to replace the momentum with gradients, imaginary gradients, right? And this becomes basically a quantum Hamiltonian. So these are Hamilton's equations. Since Hamilton's equations are first order, there is one and one's only solution to the Cauchy problem. In other words, there's only one trajectory moving forward from a point to phase space. So this is the trajectory that my system, with this particular initial condition, follows. Now, the fact that you have only one and one solution to the Schrödinger equation implies you have the trajectories never cross. This is clear for you, right? Because trajectory in phase space crossed, it means that from the crossing point, I'm writing this here, not to have to put here. From the same crossing point in phase space, you would have different ways to go, which of course makes no sense, right? The only way to go from a Hamiltonian is going backwards in time. So you can travel from here to here, or you can travel from here to here. It is very important to emphasize that at the level of the equations that we've written so far, time is reversible. So in other words, if you take Hamilton's equation and you send time to negative time, okay, the Hamiltonian doesn't change. So all you happens, you're basically working the same trajectory backwards. So the laws of physics, that, as we have described it, do not change if I change time into negative time, which is going to be a problem if we want to understand life. because life is based on irreversibility. Not only we are irreversible, in the sense that we irreversibly die, but think about any molecule that needs to process any function. It has to go back to one particular state where it performs the function. Planets don't do that. The planets keep on circulating forever. They don't return and stop until they're ready into a basin, right? They don't relax to an equilibrium and then reactivate. They keep on doing the same thing ever forever. Now, the fact that a molecule relaxes, for instance, to a given configuration is an irreversible fact. So, of course, in the back of your mind is irreversibility is linked to the concept of entropy. At some point, we will need to talk about entropy. But this is a discussion for another moment. And what I will show you is how irreversible dynamics will eventually emerge from this equation. So we will understand exactly where the arrow of time develops in macromolecular systems. It's a bit of a theoretical problem, but I think it's very interesting nevertheless, because in our education we are told that there are the laws of physics, and then magically comes this principle of growing entropy, right? Second principle of thermodynamics, which let us understand why we can order pictures like a match burning, and we can put the pictures of a match burning in temporal order, and we are given these qualitative answers, mumble jangling, it's because of entropy growth. But what we are never shown, or at least I wasn't shown at your level of education, was, okay, I want to start from an equation which is time irreversible, do a set of mathematical steps, and at some point end up with a time irreversible equation that describes the evolution of the system. And I want to see exactly when this happens. I want to see what is the origin and see what it means to be irreversible. We will do that in a couple of lectures, because this is the gateway towards stochastic dynamics for us, which is another form of dynamics, which is not Hamiltonian. Hamiltonian is deterministic dynamics, right? Completely deterministic, except that it's a fake determinism. It's a fake determinism for two reasons. It's fake because it's deterministic only if we exactly know the initial condition. And we don't know the initial condition. But it's fake also because it's fake deterministic also if we know almost exactly the initial condition. What do I mean by that? Suppose I take two initial conditions that are very close, but not exactly close. Well, it makes sense that if I follow the dynamics of these two configurations for a sufficiently short time, it will look like the trajectory of the other initial condition, right? Because after all, it evolves under the same forces, and it depends on initial condition that I can tune to be arbitrarily close to the others. So unless something highly non-linear happens at very, very short scale, highly non-analytic, smoothness of functions imposes that at least for a very short time, the two trajectories will be the same, right? But then, macromolecular system, like virtually any system with more than 3 degrees of freedom, 2 degrees of freedom even, are subject to a phenomenon called chaos. What does chaos mean? It means that there is some mathematical concept that defines chaoticity, is the so-called Lyapunov exponent, which means that the endpoint of two trajectories, which start off with an arbitrarily close initial condition, eventually diverge exponentially with this exponent. So after some time, the two trajectories go arbitrarily far from each other. This is the famous butterfly effect that you've heard about, certainly in your life. A flap of a butterfly in Brazil generates a storm in Europe. What does that mean? That you displace the initial condition by as little as possible, but let the system evolve sufficiently long, you get completely different predictions. And this is the ultimate reason why we cannot trust weather forecasts for more than just a few days. Very similar reasons. Now you find websites that promise you forecast in 15 days, but that's garbage. You can only go just a few days. In fact, if you go, the Aeronautica Militare will only give you forecasts for 3 days. That's where you think you can be reasonably accurate. Okay? Okay, so now we are facing a double problem here. We don't know the initial conditions, so even if my trajectories are deterministic, I do very little with determinism. So the problem is, how can I learn about the physical system if I cannot really do time averages for one condition? Well, here comes the ergodic assumption, and the ergodic assumption says, okay, we will reformulate it in a better form, but the spirit is, okay, if my trajectory travels so long that it visits all the important regions of configuration space so much, eventually my average will not depend very much from where I started. I lose memory of where I started, I will travel around, and eventually it will give me a result that is stable, which means that if I were to simulate the system for another 2 gazillion years, I would get the same result. And the ergodic assumptions identifies this with the next concept, which is the concept of averaging phase space, which is what I'm going to introduce right now. Okay? In a more formal way than we did last time, just mumbling the ideas. Okay, so now, the very much crucial point of everything we have said and we will say about dynamics of macromolecular systems stands in this idea of, I'm going to write it here. Oh, shit. I need to go for an eraser. So let me put this on. Okay, go back in a moment. Careful, it's still recording. So if you're going to say something, you better be quiet. Okay, very good. So the concept that we're going to describe is the density of states in phase space. So imagine to have not just one configurations, but now we look at the small volume in phase space. Okay? If I imagine to have started my Hamiltonian dynamics for all points in phase space and let the system evolve sufficiently long enough, unless this region is really unreachable for some condition, for instance, the system describes a box, and this point lies outside the box. There's no way in classical physics, with an infinite barrier or a very large barrier, that particles can penetrate the barrier and get to the outside of the box. We're not into that. Let's assume the universe is encompassed. And it's, well, clearly, my dynamics, eventually, there will be trajectory that will cross this. Now, they look like they cross, they don't cross each other. Right? But there won't be returns like this, because otherwise this would imply that trajectories in phase space cross. Right? And they are not allowed to cross under Hamiltonian dynamics. So, the trajectories that at the time t naught are in this box will evolve a little bit like a fluid. Right? They will displace. So if I count all the states that are here, d gamma, which is the elementary volume in phase space, and for each point in this volume, I look at where these points are at the later time, they will form another small volume that is somewhere else in phase space, right? Because what I've done to construct this, I've taken every point in this box, let it evolve according to the Hamiltonian dynamics, let it evolve, and before I was counting how many of these states there were in this little box, and now I'm counting them, I'm tracking them at some later time, and they form another box. It's not a box, it's some kind of shape, but it still is a shape which I can assign a volume. Now, the magic of Hamiltonian dynamics is that this behaves like the motion of an incompressible fluid. And first of all, the volume is preserved under Hamiltonian evolution. This is called the Liouville's theorem. Have you heard about that, right? Have you? Okay. But you will hear about it again for reasons of consistency. So how do we show this? Well, we compute the velocity of a phase space vector. So we look out a phase space vector changes, right? So it's not the physical velocity, because the physical velocity, number one, is three-dimensional for one particle, and this is 6-7 dimensional. It's a velocity which tells the new point in phase space subtracted from the initial point in phase space divided by the t, right? The velocity in phase space is q, depends whether I use the p's and q's first. Okay, p dot q dot. Okay, using the notation which have first the q's and then the p's. Now what I can do, I can compute another concept, which is the phase space divergence of this vector. The divergence is the sum, you know what the divergence is, so let me just write it as dp dot divided by dp plus dr dot q dot divided by dq. Now, I have a sum with all the components here, but I'm doing this one-dimensional treatment for sake of notational simplicity. I'm taking each of these and dividing by its own.
Sorry, v is the volume or the velocity?
V is the velocity of the phase space.
And why v dot is the derivative of
Oh,
velocity?
I'm sorry. You're right. Thank you. Thank you. Yeah. Of course, V is the velocity in phase space. Thank you. So this is the divergence of the velocity. Now, if I look at the divergence of velocity, and now I use Hamilton's equation, I find that this guy here is negative d by dp of dH by dq, because P dot is negative dH by dq, Hamilton's equation number 1. And this is d by dq of q dot, but q dot is dH by dP. And beautiful result for a Hamiltonian dynamics, they cancel out. But then it follows that if I look at the rate of change of an infinitesimal volume of phase space, right? I can use the chain derivative to get the total differential, right? But if I do that, I get exactly this term on the right hand side, which is 0. So I get this fantastic result, aka the Liouville's theorem, that says that the volume in which these trajectories move in phase space is conserved. Now this has, yes?
Not considering the case that where there is an unreachable part of the case, but how do we know that there are trajectories that few phase space?
There are trajectory?
That few over space.
Oh no, we won't. We will see in a moment. At the moment, all we say is this idea that I can. So I'm trying to build statistics starting from Hamilton's dynamics. I'm basically reviewing statistical mechanics 101. To do that, I'm assuming Hamilton's equation, discussing the fact that this leads to trajectories, that these trajectories behave like an incompressible fluid. Okay? Which leads to several paradoxes. One of them is the return theorem. You know, the return theorem says that if I start from one condition, if I wait long enough, I will return to that condition. Because if the system has a finite volume in phase space, and I keep on conserving the volume, I will eventually eat up all of the volume, which is somewhat contradictory because it says, okay, but so there's no really irreversible dynamics because I'm returning to an initial condition, and all sorts of things, which I will not discuss. They're all mathematicians' paradoxes because they all happen at times that are gigantic compared to any universe relevant time scales we can think of. Okay. But now the point to see, if I take now a finite volume, I can imagine that in my phase space there will be regions where the density will be larger and region where the density will be lower because the volume is conserved in phase space, but it doesn't mean that there are more or less likely regions to be visited by dynamics, depending on the initial conditions. So in other words, the whole idea here is to say, okay, I introduce a density in phase space. Rather than describing my dynamical system as a single trajectory moving in phase space, I now make the big jump, the big conceptual jump, and assuming I now have a set of possible initial conditions. And I cannot tell you what they are. I can give you a probability distribution of the initial conditions. Or if you want, an initial density of conditions. So what I'm actually doing is defining rho of t as the density in phase space, which tells me that at the initial state of the system, I don't know the velocities, I don't know the position, but I can tell that my velocity and positions were somewhere here. For instance, let's be practical. I have a particle in an harmonic oscillator. Since it's in a harmonic oscillator that is by conventionally we can set it to the origin, center to the origin. It's very unlikely that you will travel a very long distance from the origin because eventually the force will be very large and bring it back, right? Plus, the distribution of velocity that my initial condition can have is for me to decide, but typically will be within a certain range. So my initial condition will be within the range of momentum and position, right? So if I have a given density of initial conditions, and for each initial condition, I now let the system evolve according to the Liouvillean dynamics, to the Hamiltonian dynamics. This will generate a density of initial conditions, a density of phase space points in the future, right? Are you with me? So, the real question we are interested in is what is the equation for the density of conditions in the future? So what we want to do is to take the time derivative, the total derivative with respect to time of this. Well, in principle, when I do total derivatives, I've always had a partial derivative of rho, gamma of t, and t. For example, the density might change because I switch on an electric field. And this electric field will make certain configurations that were likely, less likely, right, after some time. This is an explicit dependent time. It's not a dependence on time through the evolution of the particles, right? Plus, I have my chain rule, and I will again use the notation du rho by dq by dt, q dot, still the one-dimensional notation, plus d rho by dp p dot. But I just proved you that if I count all of these states, they will be set to 0, right? The change of volume in phase space is 0. So I can set to 0 here. So in other words, I come to the equation now. Remember, this p and dot are related to the Hamiltonian, just as before. And so basically, my Liouville's equation is that this is 0, which is rewritten in terms now of the density in phase space as d rho by dt equals a guy which I call the Liouvillean operator acting on rho of x and t. And the Liouvillean is dh by dp d by dq negative dH by dq d by dp. Sorry, there's a negative sign in the definition of the Liouville. So I want to stop for a moment here and think about what we have done. We started off with a microscopic approach. We consider a bundle of initial conditions. We analyze the fact that whatever volume of initial conditions, the Hamiltonian dynamics preserves that volumes in time, which means that a total derivative of that local density, because you can put an elementary dq dv here to make this exactly the number of states in that volume, will be 0, will not change in time, and then if you spell out this change in terms of partial derivative, you get a partial differential equation that tells you how rho of gamma and t evolve in time. But now you might jump on your chair and say, hey, wait a minute. I've seen this before. Have you ever seen a partial derivative with a stochastic interpretation of a probability evolving in time according to an equation d by dt equals operators time itself? Let me rephrase. Have you ever seen in your life an equation of a quantity that will give you the probability to find the system in a place and evolves according to a time derivative time linear operator? It has the same mathematical structure of a Schrödinger equation. In imaginary time, there's no I here. So statistical mechanics contains in its stomach a mathematical structure that is very, very similar to that of Schrödinger equations, right? And it makes sense because in Schrödinger equation, you have quantum uncertainties that drives a probability interpretation through this notion of modulo square of wave function, which is entirely nonlinear and blah, 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 okay? In statistical physics, we have the fact that we have an intrinsic probability because we start off with a distribution of initial conditions, and each initial condition is deterministic. But since the initial condition, each evolution is deterministic, but since the initial condition were not deterministic, the next state of the system will be not deterministic. So I have an evolution of a probability. Okay? You start, yes.
So this is a density, right?
Yes, density in phase space.
So it's like equation of continuity?
It is a continuity equation. It is a continuity equation because it expresses the conservation of trajectories. So in other words, if a particle is obeying Newton's equation and is in some place at some time, it will not disappear. Nor it will generate two identical particles propagated in different directions. This continuity equation expresses the continuity of the fluid of trajectories, which is the conservation of mass, if you want, that comes from Newton's equation. And that's why it has the equation of a continuity equation. So this mapping from fluid dynamics and probability in Liouville's approach is rigorous. And I apologize again for saying something you have already seen in your career. But it is important to see for the first time a partial differential equation for the probability density momentum. Because this is a partial differential equation that follows directly from the Hamilton's equation, whose stochastic character is inherited from the fact that we don't know the initial condition. If we knew the initial condition exactly, this would not be a stochastic, this would be an evolution of a delta function. Because the initial condition would be a delta function in one place, and it would evolve according to a delta function. That's determinism. But since the initial condition is not a delta function, this will not evolve according to the delta function. Later on in the course, we will see another equation for the same kind of density, but it will not be a Liouvillean equation, it will be a Fokker-Planck equation that follows from intrinsically stochastic dynamics. And it will be important to see the difference between these two. Well, we will introduce stochastic dynamics, which is the landmark for doing molecular simulations. So that's why I'm spending some time reviewing Liouvillean dynamics, although I assume you have seen it somewhere. Okay, so we have laid down the Liouville's theorem, which is conceptually useful, but nobody really solved Liouville's theorem for complex systems. It's a very large dimensional. I want just to say one thing. Do you remember Hamilton's equation in quantum mechanics? Heisenberg equation, sorry. Where you have an operator and you look at the time evolution of an operator, and on the right-hand side you have a commutator. Here, I have a very similar equation because I have a time derivative of a density, not an operator. And on the right-hand side, I have something that looks a little bit like a commutator because you see I have something with a difference with a negative sign. And in fact, these are called Poisson brackets. And if you see them, they really are looking like a commutator that looks like a commutator of quantum mechanics. So if you can think of translating quantum mechanics, classical mechanics into quantum mechanics by changing Poisson brackets into commutation relationship. But this is a idea for theorists, not for biophysicists, so to say. Okay, physicists are welcome to have any mathematical concepts they want, but this is not key for them. Okay, so now, with all this in mind, what about ergodic assumption? Now we are ready, because you see, the ergodic assumption now can be given a strict mathematical definition, not strict, but a better mathematical definition, and it's the following. Suppose I let the Liouville equation do its job and evolve my initial distribution for sufficiently long time. It's common experience that for many systems that are isolated, after some times, these probabilities stop changing with time. They relax to a stationary distribution, which is equivalent to say that this guy here has a zero eigenvalue. Right? If the Liouvillean operator has a zero eigenstate, operator times eigenfunction gets zero, which means that there's no change in the distribution. Okay? How do we know? Well, at the moment, let's take it as an assumption. I will not go into the formalities of statistical mechanics, which have all these theorems of where ergodicity is preserved. We are not interested in formal aspects of statistical mechanics, in these formal aspects of statistical mechanics here. I will rely on your intuition. I take a coffee, I drop some hotter coffee in a corner, or even better, I touch my bath. It's too hot. I pour some water and I go around. Now, in the presence of gravity, things change. Actually, there would be like heavier water down and hotter water above. But let's suppose gravity is not there. I'm on an international space station, and I'm having a bath. That's a very bad example, but it's a familiar effect that if I come back after many minutes, the water is sterilized. Right? So this means that the probability distribution of finding molecules in the bath at a given momentum has come to a stationary distribution. Right? No convective motion, nothing. And it doesn't have to be uniform, like in the bath, it's not uniform. There's cold water below, hot water above, and that's still. Now, if there are convective motions, because then that means that there's a change of energy, then the water on top gets colder, goes down, and the one below goes up. That's another story. So there are situations in which the system doesn't go to a stationary distribution. And physically, this often involves exchanging heat with another system, right? That provides, for instance, the energy to perform convective motion. So, if we assume that this goes to a stationary distribution, it means that at some point I have a stationary distribution that doesn't depend on t anymore. So at some point, rho of gamma of t converges to some rho naught of gamma only. Now, if this happens, then clearly any average, any time average I do, and any will let the system visit all possible states in my system. So eventually, if I count how many times I have visited the configuration starting from one place, I will get some density. But if I slightly displace the initial condition, I will get another density, another density, another density. So now we finally understand how to identify space average and time averages. In reality, this is the result of averaging over many initial conditions that I don't know. So the result of averaging, the limit of time averages, I don't know the initial condition, can be compensated imagining that if I had averaged over many initial conditions, I would have generated a probability distribution in phase space. And now any observable can be made, any average at equilibrium, any average at equilibrium can be seen as integral in phase space of the phase space equilibrium distribution and my phase space dependent observable. Okay? Now, if you want, the ergodic assumption is if I start from a the practical way of thinking the ergodic assumption, not the statistical mechanics formal way of doing it. The practical way of thinking of ergodicity is if I take a representative ensemble of initial condition, I let the system evolve in time, I take time averages. It's equivalent to being able to access directly this distribution and perform phase space averages. Right? Do you follow me? So, why is this relevant? Because what molecular dynamics really does for you is getting you time averages. Because you evolve the system in time. But what you're really interested in statistical physics is the Liouville's density, because that's the only thing that makes sense if you don't know the initial condition. And I want to stay on this point because it's the most important of all. If I'm looking at an isolated system on which I have full control, the most fundamental object I can think of is the Newton's equation, because I can fix the initial condition and let it evolve. But if I don't have control on all the initial conditions, the Hamilton's equation or Newton's equations are meaningless by themselves. They don't describe, because even if I have one initial condition, it will describe the evolution of my initial conditions, so where? Conversely, I have a distribution initial condition, and I let Hamilton do this job, I will naturally be led to a Liouville's equation. And the Liouville's equation will give me the evolution of probabilities. So as soon as you have uncertainty on the initial conditions, your most fundamental way of formulating in classical mechanics, consistent with Hamilton's equation, the dynamics, is not through single particle evolving, but through phase space volumes evolving, phase space distributions evolving. Do you agree? And why do I insist on this? Because you open scientific journals and you read statements like this. I wanted to test the stability of this protein I prepare the system in the initial configuration and run 1 microsecond of molecular dynamics, and I saw that the protein did not change its configuration. Hereby, this configuration is stable. Okay? From the statistical mechanical point of view, this makes no sense. This equals garbage. Statistical mechanics says, don't do that. Don't do that. Don't make any statement based on finite dynamics starting from an initial condition. One trajectory doesn't represent dynamics. Statistical physics says phase space is the minimal description you have, and phase space distribution is your object of interest if you don't know to infinite accuracy the initial conditions. You only distribute the initial conditions for a system that is larger. So what you have to do is to have enough trajectories to infer the phase space distribution at some later time. Right? So for instance, going back to my simulation example, one thing you could do, you start from an initial condition. Again, this is some observable, because it could be the position if you really want to know all the molecular coordinates, but let's say you want to know the endpoint distance of a polymer, for simplicity. And you run a molecular dynamic simulation, you randomize the initial velocity, you get one collection of initial velocities, right? You apply the leapfrog formula that I told you before, with some caveats that we will need to discuss to account for temperature and pressure and blah, 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 which we will discuss better in another lecture. And you will get one and only trajectory, right? Is this enough to say something about your system? Hell no. Hell no. The least you can do is to change your initial condition according to the same distribution that you think is relevant. For instance, if you know that the system is going to start from the very same location because you prepare it like that, and you were ready to neglect small spatial displacements in the initial condition because you at least have to randomize the velocities, because those you don't know, the initial velocity. They come from the collisions, for instance, with the water around it, right? So from the phase space point of view, you are in a different point, right? And this corresponds, for instance, in phase space, if this is P and this is Q, well, you basically be getting a very small Q and a relatively large set of P's, right? So your initial place position was this, and you have your trajectory. You take another position here, which might give you another trajectory. And if you stop after the same time, and you do this for a sufficiently large number of objects, you will get the distribution of the changing distribution of this guy after a time t. You will get the distribution evolved to a finite time interval t. And for that, you can compute averages. So there's a surprising analogy. We have learned, once we learn classical physics, we are spoiled by cannonballs flying and computing exactly the landing distance, and then we go 1 year beyond, we go to quantum mechanics, and they say, forget about that. That what you were spoiled in classical mechanics. In quantum mechanics, you can no longer talk about probability, about trajectories. You only have to talk about probability. Remember the good times of classical mechanics. Now, forget about that. Quantum mechanics is harder. True. But even complex classical mechanics has the same feature. As soon as you go beyond two bodies, basically, where chaoticity starts to play, you are exactly in the same setting. You're not allowed anymore to focus entirely on a single trajectory. Everything that really makes sense is density of probabilities, which in practice means if your only tool is performing molecular dynamics, do a hell of a lot of molecular dynamics simulations. Right? And then reconstruct histograms, like you're doing, out of it. Okay? So, either we are interested in equilibrium, or if we're interested in non-equilibrium, say, I want to understand what happens on average a little bit after I unfold the protein and I let it evolve. Of course, if I wait long enough, the protein will go to its native state, the Amphi's and famous finding, assuming this is a globular protein, not an intrinsically disordered protein. And it will oscillate outside the cellular environment. It will oscillate between native and denature with certain probabilities, because every so often it spontaneously unfolds. And given the temperature, we know what is more probable. Typically, it's if you're below the folding temperature, is the native state. And fine, you go back, you know your probabilities, distributions, and you know the relative free energy of the states, right? That's equilibrium. That's thermodynamics. And you can use this to compute the relative heat, the specific heat, or whatever you're interested in. The work, and do all the things you want. But you might be interested in say, okay, now I do non-equilibrium dynamics. I unfold the protein, say with the optical tweezer, then I release the tweezer and I watch the system recollapse, right? For instance, optical tweezer measure the endpoint distance. Now, what you're actually doing in that case, you're monitoring the endpoint distance d, which is a function of the phase space, specifically is a function of the coordinates, specifically is the function of two coordinates, where the handles are attached. And then you monitor in time the evolution of the probability of finding the system at the given endpoint distance, right? So you basically are, what you do is your average value of d as a function of t is the average in phase space of rho of phase space t times d as a function of rho of phase space. What is written here? The distance between the two endpoints of my polymer, d, is a function of phase space. Well, it's not a function of momentum. It's only a coordinate, but coordinates are part of phase space. It's like say there's something depends on x or y, but it happens to depend only on x. Right? Do you follow me? If you have something that depends on positions only, it's like it depends on phase space, but it just doesn't depend on some components of phase space that are the momenta. Okay? So what you're actually doing when you want to predict something like the evolution of the endpoint distance of a polymer that collapses, you are measuring, you're computing the average of your observable, which is a function of phase space, average with the distribution in phase space of that phase space configuration that evolves in time. In practice, this will evolve starting from some initial configuration, right? So some initial distribution, for instance, everything stretched out, randomized momenta, right? And so what you want to do, if you want to evaluate that in molecular dynamic simulation, you sample your initial momenta from this randomized distribution of momenta, and you generate many, many trajectories in which you evolve for a time t. This will generate the Liouvillean trajectories, and you will allow you to infer from central limit theorem this average. Right? You know what's the central limit theorem? It's the way you can replace averages with arithmetic means with averages in the large number of numbers. Well, you know the central limit theorem. I'm not going to discuss that. Okay? So you're basically replacing this with an average. So that's what you can do. You cannot do less than that. You cannot be more ambitious than that. That's what I'm saying. And of course, you reduce to determinism in the moment where the initial distribution which determines this evolution becomes a delta function in phase space. And then the Liouvillean dynamics of a delta function will be a delta function, because we know that for a given initial condition, there will be only a given trajectory. But now I return to my first lecture. Does it make sense to talk about delta function in physics? No. So Newton's equation alone makes no sense. So it's not true that quantum mechanics determines the loss of determinism. It was lost to begin with. There was no determinism. It was an illusion. Of course, if I have a cannonball and I shoot it, I can predict with a very good accuracy that is far more accurate than I ever need the landing point. Which means that the spreading of this distribution in momentum and phase space is so small that I can neglect it. But it doesn't mean it isn't there. So there could be situations in which this distribution are very narrow Gaussians, and they remain very narrow Gaussians for a long time. But for most relevant systems that we can worry about in life, in complex systems, as soon as we become a little bit ambitious, forget about determinism. There is no determinism in physics. For 99.99999% of the problems I can worry about. So there is not really a fundamental loss there is a fundamental loss in quantum mechanics, but not really a truly practical loss for many applications. We still have to deal now with uncertainty. Now, this idea that real systems behave like quantum mechanical systems will become mathematical in a few lectures, where we will reformulate the classical dynamics of complex systems as an effective Schrodinger equation, showing that this mapping is actually there. There's not going to be any phase. That's the only real difference. There's not going to be any complex variable. Everything's going to be classical. But everything that I've done today will be reformulated in a way that is exactly mapped into quantum mechanics. And that's not by chance. It's because anytime you have sufficiently many systems, you introduce by construction stochasticity. Okay? Other questions so far?
These are still theoretical introduction, but is I don't say, but computationally we will do, I don't understand, like some.
So, yeah, so let me try to rephrase a point. The purpose of any statistical mechanics application is not to know the configuration of a system. It's to know a distribution in phase space. We might consider only distribution in coordinate space if we think the momentum components is trivial. For instance, in many cases, the distribution of velocities will be Boltzmannian, meaning Gaussian, some Maxwellian, sorry, not Boltzmannian, which is something that we will discuss in a moment. So I don't really care exactly I know that I can always use, I know how to generate momenta that look reasonable. So I might be interested only in configuration space, but I will only be interested in distributions. Okay, that's the statement number one. So now, even if I have a tool like a molecular dynamics integrator with leapfrog or more advanced algorithm, as I will discuss in a moment, even if I have that tool, those tools, my goal will not be that of predicting the state gamma, but to predict the density of states rho gamma at any time, right? And how do I do that? Well, I must consider a bundle of initial conditions and see where this bundle of initial conditions, which is the initial distribution, evolves. And I will infer that evolution statistically by central limit theorem, meaning I will sample the initial condition of molecular dynamic trajectories from that distribution, follow the evolution, for instance, the Hamiltonian evolution, get a distribution of point after some time, and by histograms, basically, infer the final distribution. Or better, I will be interested in averages, which I could do without histograms. Okay? And that's the only thing I can do.
But basically here we do the average on the final time.
At any time we want.
Yeah. Suppose it's the time we want to do the average. But like when we did the product assumption this time, I don't know, we said that the time average under the value assumption is equal to the free space alert?
Yes, only at infinite time.
Okay. So
Only at infinite time. Which means if the system equilibrates, and I can let the system go around many, many times, explore, losing memory, and have an infinitely long trajectory, that will basically visit all the configurations many, many, many times, so very, very close to it, and then I can replace. So in other words, only at equilibrium I can make statements in which time averages and, okay? But what is the static distribution? So let's assume the ergodic assumption, and there is a static distribution, rho naught of gamma. What is it? That's a very valid question, right? Answer. Well, here where Mr. Boltzmann taught us something, right? He said, okay, the contribution to science of Mr. Boltzmann is manifold, but the most important is this idea of notion of equilibrium ensemble. So basically the idea there are equivalent copies of the system, each with the probability, and basically being able to derive the probabilities at equilibrium in some cases. And the cases that we usually are taught in the undergrad educations are systems that conserve energy, systems that preserve temperature, right? But conserve number of particles, called the canonical ensemble, and systems that preserve temperature but don't preserve the number of particles, aka the grand canonical ensemble. The names that have no idea why they come this way, right? You've heard these names. Systems that conserve energy are called, remember that? Microcanonical. Now, this is something you should remember. And so the first thing I want to do is define for you the microcanonical ensemble. The microcanonical ensemble says my system evolves according to Newton's equations and is isolated, right? Newton's equations are energy conserving, or aka symplectic, which means that whatever the energy was at time zero, it will remain the same. Right, now I'm going to spit result for the moment. I'm not going to prove these results yet, because I will use a different approach than the one that you used to prove it, since we want to make contact with AI at some point. So we use a formalism that is more close to that of AI. This is AI in statistical physics of macromolecular systems. So I would use a Shannon entropy principle, maximum entropy principle, which is often used in inference and AI, along with Bayesian statistics, to derive these results, or one of these results. But at the moment, let me just state this, right? If you might remember that this will give me so basically what this is telling me that in the microcanonical ensemble, this is my configuration space. I can think about a hypersurfacing configuration space that only collects points with the same hamiltonian or same energy. And if I wait long enough, my system will uniformly distribute on this that is called the ergodic surface. Remember that? So the system will travel at constant energy and eventually populate all the states of fixed energy with equal probability in the long time limit. Okay? But I might say, but rather than fixing the energy, I fix the expectation value of the kinetic energy, the average value of the kinetic energy in the system, aka the temperature, right? That's 1/2 kT. Right? So if I a surface with constant energy will give me the ergodic surface. A distribution with constant average value of the momenta you know, it's equivalent to putting your system in contact with a heat bath that will exchange heat but will maintain the temperature constant. And this will be given, what will this give me if I fix the temperature? Well, the famous canonical distribution. Right? But H is the Hamiltonian, beta is 1/kT. Right? Remember that? And finally, I'm just spitting results. I'm not trying to convince you of anything. I'm just recompiling things that are in books because we're going to think about them and rederive at least some of them, particularly this one, from a entirely different perspective in a while. Okay. And finally, if I have a distributions and I don't fix neither the energy, but I fix the average kinetic energy, and neither the number of particles, but I fix an average number of particles through a parameter called the chemical potential, I get what is called, so fixing mu and t, I get the ground canonical, which is basically a Boltzmann distribution with an exponential prefactor which contains the number of particles times some kind of normalization. Now, I'm just copying definitions at the moment. I don't expect you to remember the derivation. I cannot redo all the statistical mechanical course here. I just want to flash them and emphasize one thing. In statistical mechanics, you have a theorem called the equivalence of the ensembles. Do you remember that? It mentions that basically all these ensembles, if you sample from these ensembles, but you sample a sufficiently large number of particles, you get the same averages, regardless of what ensemble you sample from. So it's just a matter of practical. Of course, you have to sample from, if you want to study a system at a given temperature, you have to sample and choose the energy that will give you exactly that temperature. Right? But in principle, if you can do that, whether you solve a microcanonical or a canonical, it doesn't really make any difference. So in principle, the leapfrog algorithm that I gave you, for large number of particles, in principle, can get you through this board, because it is supposed to solve the microcanonical, right? It's the Newton's equation, and it's supposed to conserve energy. So if I use microcanonical evolution, put a lot of water molecules, okay, the energy, if I were infinitely accurate, will stay constant, but the kinetic energy will fluctuate, right? But if I have so many particles, fluctuations are suppressed by the root of number of particles, the fluctuation will be suppressed, the relative fluctuations will be suppressed. And now, if I tune the energy so that the average kinetic energy is the temperature that I really want, I could use the microcanonical integrator to study fixed temperature. Okay? You follow me? It's not the most practical way to do things. So now, part of the study of this course will be figuring out how to achieve this sampling in a much more efficient way. By the way, let me tell you, the leapfrog algorithm conserves energy up to corrections of order delta t, right? If you if you let the system accumulate errors and errors, the energy will not stay constant. So really doing a dynamics that strictly speaking conserves energy is very expensive. You have to be very careful. It's called symplectic dynamics. It's computationally very expensive. There are much better ways, and you're not really interested in keeping the energy constant. What you're really interested in is keeping the thermodynamic coordinates constant. Pressure, temperature. So we will develop algorithms to sample this. I want to emphasize one extra point. In doing molecular simulations, we are not just interested in this ensemble, and this ensemble. We are most likely interested in another type of ensembles. Because you see, after all, the number of particles doesn't really change in a protein, right? I don't have chemical reaction going on. Certainly I don't have decay of nuclei producing hydrogens or stuff, right? So let's not worry about the ground canonical form. The ground canonical has been written here, never be spoken again, fine. Even the canonical, it's not the most natural setting because proteins or any biomolecule is typically in solution at a given temperature. There's a heat bath, right? So even the canonical, sorry, the microcanonical is not very interesting. So we really want something which has a finite temperature and a finite number of particles. But in fact, we will worry about two ensembles that are closely related. One ensemble will be one in which I have finite number of particles, finite temperature, but also, since I have a simulation box, finite volume. Which is not exactly there in the canonical ensemble as you would imagine, because you never really mention the volume so explicitly as something to be constant. You imagine there's a volume that contains the system, and that's it. For a simulation, knowing exactly what is the volume of your system is important because the system has a given volume, right? Okay. But you see, sometimes if you have a system of particles at a given temperature, at a given volume, and you compute the pressure, and we will discuss how to compute the fractions, on the walls, the average force on the wall, it will fluctuate, right? Because every so often you have more collision than others, right? So in the NTV, the pressure is not constant. But we might be interested in setting the pressure to a particular value because, hey, we live at 1 atmosphere. So we might give up some of these coordinates for the pressure. So the other ensemble we might be interested in studying is the NPT ensemble, where we give up fixing the volume, as a matter of fact, but we fix the value of the pressure. So we have on the table the menu for the next lectures. The first thing we need to do is to convince you that at least the canonical distribution makes sense. And you know it from your background education, but I want to revisualize that in the eye of a principle that is deeply used in today's AI applications. So that whenever you will read an AI paper and you will read about this, you know what we're talking about. And it's the concept of Shannon's entropy, an entropy of information. And we will see that the canonical ensemble follows from a maximum entropy principle as the most unbiased ensemble with fixed temperature. Okay? So we understand why the canonical has. So this is an approach that doesn't require heat bath, as weak coupling between the heat bath and the system, and then doing microcanonical for the universe and splitting the contribution. Remember the derivation of the canonical ensemble. This is purely statistical, and it's information theory based. Okay, that will tell us how to do canonical without worrying about volume, but it will tell us also the principle to build any ensemble that we want. And then we will address the second question, that is, how do I drive dynamics or write modifications of the Newton's equation that don't sample the microcanonical as the one that we saw, but sample these ensembles. Okay? So we will need to change the equation of motion a little bit to ensure that at equilibrium I can sample from those examples. Okay? And that will take us a good week. Then we will stop, do simulations for a while. Oh, you will do simulations. So here is what I would like you to do. I will write it on the chat as well. I'd like you to download GROMAX, install it on your computer, do whatever it takes if you have a computer. If you don't have a computer, just let me know. We figure out a way to have you do it. But you will have to install GROMAX on your computer and install two programs. Well, one is GROMAX. And by the way, download the manual of GROMAX because there's so much about force field and ensembles. There's also basically a compendium of statistical physics. The minimum required, not as advanced as we will do, but it will be good to have it, right? And the other thing I'd like you to do is to download a program called VMD, which is a program for molecular visualization that will allow you to look at the molecule and make movies of molecule moving around. So after we have done with defining this ensemble and the dynamics of these ensembles, I will ask you to do a little simulations and see in practice what it means to sample the phase-space distribution and what it doesn't mean to sample the phase-space distribution, meaning what you should not do and what you should do instead. Okay? I think, wow, perfectly on time. Great.